Every spacecraft humanity has ever built would be dead within years if it left the solar system for good. Not because it ran out of fuel, because something essential would break and nobody would be coming to fix it. The International Space Station, the most complex machine ever assembled in orbit, requires constant resupply missions, software patches, replacement parts, and a full team of engineers on the ground monitoring every breath of recycled air. Move that station past Mars, past Jupiter, past the edge of the heliosphere, and every single one of those lifelines disappears forever. A real starship, a machine built to cross the void between stars, would need to survive not for months but for decades, centuries, or longer, with nothing behind it but the memory of Earth. If this kind of deep engineering mystery is something that grabs your attention, do me a favor and hit that like button. And if you have not subscribed yet, now is a great time. It helps the channel more than you might think, and I appreciate every one of you. Now, let's begin. Think about the longest any machine has ever operated without human hands touching it for repair. Not a satellite coasting through a stable orbit with no moving parts. Not a stone monument standing motionless in a field. A real machine. Fluids flowing through pipes, electronics processing commands, actuators firing on schedule, mechanical components wearing against each other every second of every day. The honest answer is measured in decades at best. Voyager 1, launched in 1977, is still transmitting faintly from interstellar space nearly 50 years later. It is the most distant human-made object in existence, more than 160 astronomical units from our star, drifting through the void between solar systems at roughly 17 kilometers per second. But Voyager 1 is a machine the size of a small car. It carries no crew, no atmosphere, no water supply, no food. Its radioisotope thermoelectric generators produce barely enough electricity to power a couple of household light bulbs, and that output shrinks every single year as the plutonium-238 decays. Engineers on the ground have already powered down most of its scientific instruments just to keep the communications system alive. Several of its thruster sets have degraded, forcing the ground team at NASA's Jet Propulsion Laboratory to activate backup thrusters that were never designed for primary use. A single radio message from Earth to Voyager 1 now takes more than 22 hours to arrive. Every command is sent blind, and the confirmation that it worked does not come back for nearly a full day. Voyager 1 is the most successful long-duration deep space machine humanity has ever constructed, and it is a tiny, crewless, fading whisper compared to what a real starship would need to be. Now multiply the complexity by a factor of 10,000. A real starship is not a probe, it is not a capsule, it is not a transport vehicle with a return ticket stapled to the dashboard. A real starship is a spacecraft designed to cross interstellar space and remain functional long enough to reach, study, or settle another star system. That definition sounds almost clean, almost manageable, but every single word in it conceals a nightmare. Start with the word functional. A starship is not alive just because it is still moving. Momentum in the vacuum of space is free. Once you are coasting, you coast forever. A dead ship travels at the same velocity as a living one. The difference between a starship and a coffin is not speed, it is capability. Can the ship still generate power? Can it still shield its inhabitants from the radiation pouring through the hull every second? Can it still scrub carbon dioxide from the air and recycle water from human waste? Can it still grow food? Can it still navigate with enough precision to know where it is and where it is going? Can it still communicate? If not with Earth, then at least with its own subsystems. Can it still repair the machinery that keeps all of those other systems alive? And can it still slow down when it finally reaches something worth stopping for? Strip away any one of those capabilities, and the starship stops being a starship. It becomes wreckage, with a trajectory. It becomes a steel sarcophagus, carrying the frozen remains of a mission that started with hope and ended with a failed pump or a cracked seal, or a circuit board that took one too many cosmic ray hits and never woke up. The International Space Station has spent more than 25 years teaching humanity exactly how demanding it is to keep human beings alive inside a sealed vessel. and the station floats only about 400 kilometers above the surface of the Earth. It orbits inside Earth's magnetosphere, the planet's invisible magnetic shield that deflects most charged particles from solar flares and from deep space sources. It receives resupply missions from Earth multiple times each year, spacecraft carrying food, fresh water, clothing, scientific equipment, replacement hardware, spare parts, and personal items for the crew. It is staffed by rotating teams who typically spend 6 months to 1 year aboard before returning to a planet with hospitals, gravity, and open air. The crews are backed by hundreds of engineers on the ground who monitor every system in real time, diagnose problems remotely, and ship replacement components on the next available cargo vehicle. And even with all of that support, the station's life support systems require constant attention. Pumps fail, filters clog, seals degrade. Coolant loops develop slow leaks that can take weeks to isolate. The carbon dioxide removal assembly, one of the most critical components aboard, has experienced repeated mechanical issues requiring hands-on maintenance. The water recovery system is an engineering marvel that reclaims most crew water through advanced filtration and catalytic processing, but a fraction is inevitably lost and must be replaced by deliveries from Earth. The oxygen generation system splits water molecules to produce breathable oxygen, but the electrolysis hardware wears out and must be serviced or swapped for spares. The trace contaminant control system filters volatile organic compounds and other harmful gases from the cabin atmosphere, and its sorbent beds must be periodically replaced with fresh material that arrives from the ground. Every one of these systems has a known failure rate. Everyone requires specific spare parts. Everyone depends on crew members trained to maintain it, and on ground-based engineers who understand its design history and failure modes. The station works because Earth is right there, 400 kilometers below, watching, listening, sending help. A real Starship would need to do everything the station does, plus propulsion, plus long-range navigation without ground-based tracking, plus food production at scale, plus radiation shielding far beyond what Earth's magnetic field provides, plus onboard manufacturing and fabrication, plus medical capability equivalent to a small hospital, plus waste processing at 100% closure, plus energy generation sufficient to power all of these systems simultaneously for the entire duration of the voyage. And it would need to do every single one of these things with absolutely zero external support. No resupply, no rotating crews, no software patches from Houston, no spare parts from any factory. Nothing arrives, nothing helps. Nothing fixes itself unless the crew fixes it with materials and knowledge already aboard. The ship either carries the solution to every problem it will ever face, or the problem eventually kills the mission. There is a hierarchy of difficulty in spaceflight, and most conversations about starships gloss over it. Each level introduces not merely greater difficulty, but a fundamentally different category of problem. Low Earth orbit is the first level. You are close to home. You can return in hours. Resupply flights take weeks to arrange, but they arrive reliably. Communication with mission control is essentially instantaneous, delayed by fractions of a second at most. Earth's magnetic field wraps around the station and absorbs most incoming radiation. The engineering challenges are serious but bounded and well understood. Humanity has maintained continuous human presence in low Earth orbit since the year 2000. We know how to do this. We are doing it right now. The Moon is the second level. Farther away, at roughly 384,000 kilometers, but communication delay is barely over a second each way. Resupply is expensive, but achievable. Radiation exposure increases outside the magnetosphere, but the Moon is close enough that realistic abort scenarios exist for most failure modes. If something goes critically wrong, the crew can come home. Mars is the third level, and it is where the fundamental nature of the problem begins to shift. Mars is separated from Earth by distances ranging from roughly 55 million kilometers, at closest approach to over 400 million kilometers, when the planets are on opposite sides of their orbits. Communication delay ranges from about 4 minutes to over 24 minutes one way, which means a round-trip conversation with mission control can take nearly an hour. A crewed Mars mission requires roughly 2 to 3 years from launch to return, including months of transit each way and a stay on the surface timed to the orbital mechanics of both planets. Resupply during the mission is not practical. The crew must carry or produce almost everything they need for the entire duration. Radiation exposure during the interplanetary transit is significant, accumulating over months spent outside any planetary magnetic field. And for the first time in human spaceflight, medical emergencies cannot be resolved by evacuation. If a crew member suffers a cardiac event or acute appendicitis on Mars, they are treated with whatever medical equipment exists aboard the habitat, or they are not treated at all. Mars missions introduce the concept of no rescue as a lived reality rather than a theoretical edge case. But even Mars, as brutally difficult as it will be, remains within the solar system. The nearest star is still a source of usable energy. Communication with Earth, although painfully delayed, still functions. The journey is measured in months, not lifetimes. The crew knows, at some fundamental psychological level, that they are coming home. Interstellar space is not the next step up this ladder. It is a different ladder entirely. Beyond the heliosphere, our star shrinks to a point of light no brighter than any other. Solar panels produce nothing. Communication with Earth, if it remains possible at all, suffers delays measured in years or decades. A message sent home today arrives after the sender's children have grown up. A reply, if one comes, describes an Earth that has changed in ways the crew cannot predict. There is no resupply, no return trajectory, no abort option, and no rescue mission under any combination of circumstances. The radiation environment shifts from the intermittent hazard of solar particle events to the relentless, omnidirectional bombardment of galactic cosmic rays. These are high-energy particles, protons, alpha particles, and fully ionized heavy nuclei of elements like iron, carbon, and oxygen, accelerated to significant fractions of the speed of light by supernova remnants and other violent astrophysical processes across the galaxy. They penetrate meters of solid material, they shatter DNA strands, they flip bits in computer memory, they degrade the molecular structure of polymers, lubricants, and seals. And unlike solar storms, which come in bursts that can be predicted and sheltered against, galactic cosmic rays never stop. Every second of every day, of every year of the voyage, the ship and everything inside it absorbs this invisible, ceaseless bombardment. The duration of an interstellar voyage, even to the nearest neighbouring star systems, is not measured in months but in decades at minimum. More realistically, it is measured in centuries. At 10% of the speed of light, a velocity that is vastly beyond anything humanity has ever achieved or is currently capable of building, a journey to Alpha Centauri, the nearest star system at roughly 4.4 light-years, would take approximately 44 years. 10% of light speed means roughly 30,000 kilometers per second. That is nearly 3,000 times faster than any crewed spacecraft has ever travelled. No propulsion system that currently exists, that is under funded development, or that has passed beyond the conceptual stage, can accelerate a crewed vessel to that speed. The most ambitious propulsion concepts ever studied with any grounding in real physics, designs like the 1970s-era Project Daedalus, propose speeds of roughly 12% of the speed of light, but only for an uncrewed probe with a total mass far below what any crewed vessel would require. At more achievable speeds, perhaps 1 to 5% of the speed of light, Alpha Centauri becomes a journey of roughly 100 to 450 years. Those are not abstract numbers, those are the lifespans of entire civilizations. Even the Roman Republic itself lasted barely 500 years. The Ottoman Empire rose and fell within a comparable span. A starship crossing to even the nearest star at 1% of light speed would need every critical system aboard: life support, power, propulsion, shielding, navigation, computing, food production, and maintenance infrastructure to function reliably for longer than most nations have existed. No machine humanity has ever built comes within an order of magnitude of that requirement. This is where SpaceX Starship becomes genuinely useful as a comparison, not because it has anything to do with interstellar travel, but because it represents the absolute cutting edge of what human launch engineering can achieve right now. It shows us how far the cutting edge is from the actual problem. SpaceX Starship is the most powerful launch vehicle ever developed. Its super-heavy first stage is powered by 33 Raptor engines, burning liquid methane and liquid oxygen. As of the middle of 2026, the full Starship system has launched 12 times, with 7 successful flights and 5 failures. The most recent flight was the first test of the version 3 configuration, introducing Raptor 3 engines and numerous structural improvements. SpaceX is constructing enormous manufacturing facilities at both its Starbase site in Texas and at Kennedy Space Center in Florida, building multiple launch pads with the goal of reaching a launch cadence unlike anything the space industry has seen before. The engineering ambition is extraordinary, but SpaceX Starship is designed for Earth orbit, for deploying large satellite constellations, for lunar cargo and crew delivery as part of NASA's Artemis program, with the first crewed lunar landing currently targeted for 2028, and eventually for transporting cargo and crew to Mars. Its missions are measured in hours for orbital flights, in days for lunar operations, and in months for Mars transit. It depends entirely on ground infrastructure for launch, catch, and refurbishment. It depends on orbital refueling, requiring multiple tanker flights to fill the spacecraft's propellant tanks before it can depart for the Moon or Mars. It depends on mission control in real time. It depends on Earth for every replacement part, every engine swap, every tile repair, every software update. None of this diminishes the achievement. SpaceX Starship is solving one of the great engineering challenges of our time, making access to space routine, reusable, and affordable. But it is solving a fundamentally different problem than interstellar travel. The gap between Starship and a true interstellar vessel is not a gap of degree, it is a gap of kind. Starship is a truck, a revolutionary, reusable, brilliantly iterated heavy-lift truck designed to haul cargo and crew between Earth and nearby destinations within the solar system. A real Starship is a sealed, self-sustaining world. The difference is the difference between a cargo ship that crosses the Atlantic Ocean in 2 weeks, with ports on both ends, and a submarine that must remain submerged, self-sufficient, and fully operational for 500 years with no port anywhere on the planet. And this is the realization that changes every conversation about reaching the stars. The question most people ask about starships is the wrong question. They ask how fast it can go. Speed matters. Of course it matters. Faster speeds reduce travel time, which reduces the number of years every system aboard must survive. But speed is not the bottleneck. The bottleneck is survival. The correct question is not how fast the Starship can travel. The correct question is how long the entire ship, every system, every subsystem, every wearable component, every crew member, every piece of institutional knowledge required to keep the machine running can remain alive enough to still count as a Starship. Because a Starship does not fail the way a rocket fails. Rockets fail in fire. Rockets explode on the launch pad or break apart during ascent, or tumble out of control during re-entry. The failure is dramatic, immediate, and unmistakable. A Starship fails the way a human body fails. Slowly, quietly, one organ at a time. A water recycling membrane degrades by 3% per year. After 10 years, the system runs at 70% efficiency. After 20, it drops below the minimum threshold needed to sustain the crew without supplemental water reserves. But there are no supplemental reserves. There is only what the ship carries and what it can recover. The crew begins rationing. Hygiene standards drop. Crop irrigation is reduced. The hydroponic bays produce less food. Caloric intake falls. Immune function weakens. An infection that would be trivial to treat in any hospital on Earth becomes a crisis with no antibiotics left in the pharmacy locker. Meanwhile, a bearing in the main atmospheric recirculation fan develops a wobble. The vibration worsens over months. The crew identifies the problem, but the replacement bearing requires a specific alloy machined to a specific tolerance, and the onboard fabrication shop cannot reproduce it exactly. They manufacture a close approximation from available stock. It holds for 2 years, then it fails again, and this time the vibration damages the adjacent motor housing. Now they need 2 parts they cannot make. Meanwhile, a micrometeoroid impact that occurred 3 years earlier cracked a secondary coolant line in the power generation module. The leak was slow enough to patch with sealant, but the patch material is degrading under continuous thermal cycling. Coolant levels drop. The reactor must operate at reduced capacity to avoid overheating. Power output falls by 15%. The crew must decide which systems continue running at full capacity and which are throttled back. They cut lighting in non-essential corridors. They power down one of the 2 onboard computing clusters and run the remaining one on a load-balanced schedule. They switch the atmospheric scrubbers from continuous operation to a duty cycle, running them 80% of the time. Carbon dioxide concentrations in the cabin atmosphere creep upward. Headaches begin, fatigue, slower reaction times, impaired judgment in the people responsible for making every critical decision aboard. None of these failures is catastrophic on its own. Each is manageable in the short term with workarounds and improvisation, but they compound. They interact. Fixing one problem consumes resources, crew time, and focused attention that cannot simultaneously be spent on the others. And every repair is temporary, because the replacement parts and patch materials are themselves subject to the same relentless degradation. The ship enters a slow, grinding spiral of declining capability, and somewhere in that spiral, it crosses an invisible line. The vessel is still moving. Its velocity has not changed by a single meter per second, but it can no longer sustain human life, or navigate with precision, or generate enough power to run the deceleration burn that would make arrival meaningful. It is no longer a starship. It is a relic travelling at enormous speed through absolute darkness, carrying the frozen remains of a mission that ended not because its crew lacked courage, but because a bearing wore out and nobody aboard could manufacture a replacement. This is what interstellar travel actually demands when you strip away the science fiction. It is not a story about engines and fuel and thrust-to-weight ratios. It is a story about seals and filters and lubricants, about the molecular stability of pharmaceutical compounds stored for 50 years in a high-radiation environment, about the corrosion rate of aluminum alloys in recycled and reprocessed atmospheres, about whether a 3D printer loaded with metal powder can manufacture a turbopump impeller with the metallurgical precision required to survive 10,000 hours of continuous operation without catastrophic fatigue cracking, about whether the great-grandchildren of the original crew will still be able to read the engineering manuals written by people who have been dead for a century. A real starship is not a faster rocket. It is a machine that must simultaneously function as a spacecraft, a habitat, a power plant, a repair shop, a hospital, a farm, a radiation shelter, a computer network, a navigation system, a manufacturing facility, and a miniature civilization. No single machine in human history has ever been required to serve all of these roles at once. No machine has ever been asked to do it for decades or centuries without any form of external support. And no machine has ever had to do it in an environment where the nearest source of help is not just far away, but receding at the speed the ship itself is travelling, growing more distant with every passing hour. The reason this matters, the reason this is not simply an exercise in engineering pessimism, is that every serious conversation about reaching the stars eventually crashes into this wall. You can design the most elegant propulsion system ever conceived. You can solve the fuel problem. You can find a way to accelerate a vessel carrying 1,000 people to 5 or 10% of the speed of light. And none of it makes the slightest difference if the water recycler fails in year 37 and nobody aboard can repair it. Distance is not the primary enemy. Time is the enemy. And time attacks everything aboard the ship simultaneously, patiently, without pause and without mercy. A starship does not race toward a destination. It endures toward one. Every system aboard is a clock counting down. And the question of whether any destination in the galaxy, Alpha Centauri, Tau Ceti, or any other point of light in the sky, is genuinely reachable depends entirely on whether every one of those clocks can be kept running long enough for the distance to shrink to zero. That is the question this story exists to answer. Not how fast, not how far. How long can the whole machine survive? And the answer begins with the systems that would have to keep it breathing. A starship breathes, not in any biological sense, but in an engineering sense that is just as fragile and just as fatal when it stops. Every sealed habitat that carries human beings must continuously remove the carbon dioxide they exhale, replenish the oxygen they consume, filter the trace contaminants that accumulate from their skin, their equipment, their food, their waste, and the slow outgassing of every polymer, adhesive, and sealant in the structure around them. On the International Space Station, this process requires an interconnected network of chemical scrubbers, electrolysis units, catalytic oxidizers, and trace contaminant control assemblies. The system works. It has kept crews alive in low Earth orbit for more than 25 years, but it works the way a hospital ventilator works. Reliably, as long as someone monitors it, maintains it, swaps its consumable components, and replaces any module that fails using parts delivered from the ground. A real Starship would need to perform exactly the same atmospheric management, except with no deliveries. Ever. The carbon dioxide removal system aboard the station uses zeolite sorbent beds that must be periodically baked out to regenerate their absorptive capacity. Those beds degrade over time. Their molecular structure slowly changes under repeated thermal cycling. After several years, regeneration becomes incomplete, and the beds must be replaced with fresh material. On the station, that replacement material arrives on the next cargo flight. On a Starship, it either exists somewhere in the ship's inventory of spares, or the crew must manufacture a substitute from raw materials aboard, or carbon dioxide levels in the cabin begin to climb. The effects of elevated carbon dioxide on human cognition are well documented and begin at concentrations far below what most people expect. At roughly 1% atmospheric concentration, crew members experience headaches, fatigue, and difficulty concentrating. At 2%, judgment and decision-making degrade measurably. At 5%, the symptoms become severe: dizziness, confusion, rapid breathing. Above 8%, unconsciousness follows within minutes, and death shortly after. The difference between a functioning Starship and a dead one can be a chemical scrubber that is 3% less efficient than it was a decade ago. That margin is the margin of survival. Oxygen generation presents a parallel problem. The station produces breathable oxygen through electrolysis, splitting water molecules into hydrogen and oxygen. The hydrogen is fed into a Sabatier reactor that combines it with carbon dioxide to produce water and methane, partially closing the atmospheric loop. But electrolysis cells and reactor catalysts degrade, and the entire process depends on a reliable supply of water and electricity. If either drops below threshold, oxygen production falters. The crew does not suffocate suddenly, they suffocate gradually, over weeks, as the partial pressure of oxygen in the cabin drifts downward and the atmosphere becomes subtly but progressively less able to sustain conscious human activity. The air aboard a Starship is not a resource you load at departure and forget about. It is a living system, a chemical equilibrium maintained by machines that must operate continuously for the entire voyage. Every breath the crew takes shifts that equilibrium slightly. Every exhalation adds carbon dioxide and moisture and volatile organic compounds. The machines pull the atmosphere back toward habitability with every cycle. If the machines slow down or lose efficiency, the atmosphere drifts. And in a sealed vessel with no outside air supply, there is no margin for drift. The air is either maintained or the crew is dead. There is no middle state. Water follows the same logic, but with its own distinct nightmares. A human being requires approximately 2.5 to 3 litres of drinking water per day. Additional water is needed for food preparation, hygiene, and crop irrigation if the ship grows its own food. The International Space Station's water recovery system processes crew urine, humidity condensate from the cabin air, and other wastewater through a series of filters, distillation processes, and catalytic treatments to produce potable water. The recovery rate has reached approximately 98% following recent upgrades, an impressive figure. But that remaining 2% must still be replaced by water delivered from Earth on resupply missions. On a Starship, every molecule of water aboard at departure is the total supply for the entire voyage. Even if the system launches at 98% efficiency, decades of filter degradation and catalyst exhaustion will erode that figure. If the recovery rate slips to 90%, the ship loses 10% of its water with every full cycle through the crew. Over months, that loss is manageable from reserves. Over decades, it becomes existential. A Starship's water recovery system must approach effectively 100% closure, and no system built by human beings has ever achieved that at the scale required to support a crew for a multi-decade mission. Every filter membrane in the system has a finite lifespan. Every pump seal wears, every catalytic bed loses potency, and every replacement component must come from onboard stores or onboard manufacturing because there is nowhere else. Water also plays roles that most people never think about. It moderates temperature in thermal management loops. It serves as feedstock for electrolysis to produce oxygen. It is a component of radiation shielding in some proposed designs, with water walls or water-filled structural elements absorbing incoming particles. It is the growth medium for hydroponic crops. It is the solvent in which most of the ship's chemistry operates. Lose water, and you do not just lose drinking supply, you lose thermal control, oxygen generation, food production, and shielding simultaneously. Water is not a commodity aboard a starship. It is a structural element of survival, and every drop that escapes the closed loop is a drop that never comes back. Food production at interstellar scale introduces biological complexity on top of the mechanical and chemical challenges. Carrying all food from departure is possible for short missions but collapses under the math of longer voyages. A single crew member consuming 2,000 calories per day requires approximately 730,000 calories per year. For a crew of 100 over a 50-year voyage, the total caloric requirement exceeds 3.6 billion calories. Converting that into stored food by mass yields figures in the hundreds of tons, even before accounting for packaging, preservation, and spoilage. And stored food has shelf life limits. Freeze-dried meals degrade nutritionally over years. Vitamins break down. Fats oxidize. Proteins lose bioavailability. A crew eating 20-year-old rations may technically have food, but they may not have nutrition. The alternative is bioregenerative life support. Growing food aboard the ship using hydroponic or aeroponic systems lit by artificial light powered by the ship's reactors. Plants would serve a dual function, producing edible calories while also absorbing carbon dioxide and releasing oxygen, partially closing the atmospheric loop. The European Space Agency's Melissa project and NASA's crop growth experiments aboard the station have demonstrated that plants can grow in controlled environments in space. But the results have been mixed. Crops grown in microgravity have shown abnormal growth patterns, diminished yields, and in some cases a failure to produce viable seeds. Root zone management, nutrient delivery, pollination, pest control, and lighting energy costs all present engineering challenges that scale dramatically with crew size and mission duration. A starship's farm is not a garden. It is a biological machine that must produce a specific caloric and nutritional output every single day for the entire voyage. A single crop failure, whether caused by a fungal contamination, a lighting system malfunction, a nutrient imbalance in the hydroponic solution, or a subtle shift in the atmospheric composition of the growing chamber, can cascade into a food shortage that takes months to recover from. And during those months, the crew eats from reserves that are finite and irreplaceable. The margin between a functioning agricultural system and starvation aboard a starship is thinner than most engineering discussions admit. Radiation shielding is the survival problem that has no elegant solution at any currently understood level of technology. In interstellar space, outside the protective bubble of any star's magnetic field, the dominant radiation hazard is galactic cosmic rays. These are not the relatively low-energy particles of the solar wind. Galactic cosmic rays include protons, helium nuclei, and fully ionized heavy nuclei of elements like iron and silicon, accelerated to enormous energies by supernova remnants, neutron star collisions, and other violent astrophysical processes scattered across the galaxy. Some of these particles carry energies measured in billions of electron volts per nucleon. They penetrate meters of solid material. They cannot be fully stopped by any practical thickness of passive shielding that a spacecraft could carry. The physics is unforgiving. When a high-energy heavy ion strikes a layer of shielding material, it does not simply stop. It shatters, producing a spray of secondary particles, neutrons, protons, pions, and lighter nuclear fragments that can be as biologically damaging as the original particle. This is called nuclear spallation, and it means that simply piling on more shielding material does not always reduce the dose to the crew. Beyond a certain thickness, Additional shielding can actually increase the secondary radiation inside the habitat. Studies using Monte Carlo simulations have shown that hydrogen-rich materials like polyethylene and carbon fiber reinforced plastic outperform traditional aluminum shielding because lighter nuclei produce fewer dangerous secondary particles. But even optimized shielding materials at practical thicknesses of 20 grams per square centimeter reduce the effective dose by only roughly 30 to 50%. The numbers behind this are stark. In unshielded interstellar space, a crew member would accumulate a radiation dose on the order of several hundred millisieverts per year from galactic cosmic rays alone. With optimized passive shielding, that dose drops but remains in the range of several hundred millisieverts per year. Over a 40-year voyage to Alpha Centauri, cumulative dose could reach multiple sieverts. Current career dose limits for astronauts set by space agencies are typically in the range of 1 sievert. Beyond that threshold, the statistical risk of radiation-induced cancer rises steeply. On a multi-decade or multi-century voyage, every crew member aboard is essentially guaranteed to accumulate a dose well above any limit that any space agency on Earth currently considers acceptable. Active magnetic shielding, using superconducting coils to generate powerful magnetic fields around the habitat, has been proposed as an alternative. The concept is sound in principle. Charged particles follow curved paths in magnetic fields, and a sufficiently strong field could deflect most incoming cosmic rays before they reach the hull. But the engineering requirements are formidable. Proposed designs call for superconducting magnets, generating fields of several tenths of a Tesla across volumes large enough to enclose a crewed habitat. The magnet systems would require substantial mass, continuous cryogenic cooling, and enormous electrical power. They would need to operate without failure for the entire voyage, in an environment where any quench, a sudden loss of superconductivity, would dump enormous thermal energy into the structure, and they would provide no protection against neutral particles like neutrons, which carry no charge and are unaffected by magnetic fields. Active shielding remains a concept study, not a validated engineering solution. The radiation problem aboard a Starship is not a crisis that arrives suddenly. It is a permanent condition. It is like standing in a hailstorm that never stops, where the hailstones are invisible and pass through walls. You cannot run inside. You are already inside. The hull is the best shelter you have, and it is not enough. Every day, every crew member accumulates damage at the cellular level. The DNA in their cells absorbs hits. Repair mechanisms fix most of the damage, but not all. Over years, the errors accumulate. Cancer rates climb, cataracts develop, cardiovascular disease risk increases, cognitive function may degrade. The crew does not drop dead from radiation. They age faster. They get sicker more often. They lose resilience. The ship's population becomes progressively more fragile, and the medical system that must care for them has no hospital to refer patients to, and no pharmaceutical supply chain to draw from. Power generation is the system that makes every other system possible, and it is the system with the hardest scaling problem across interstellar distances. In the inner solar system, spacecraft rely on solar panels. At Earth's distance from our star, sunlight delivers approximately 1.36 kilowatts per square meter. At Jupiter, that drops to roughly 50 watts. Beyond Saturn, solar energy becomes effectively useless for powering anything more demanding than a small probe's housekeeping electronics. In interstellar space, there is no sunlight. There is no star. There is nothing but the faint, cold background glow of the cosmic microwave background radiation, which carries effectively zero usable energy. The only proven long-duration power source for deep space missions is nuclear. Radioisotope thermoelectric generators, which convert the heat from radioactive decay of plutonium-238 into electricity, have powered spacecraft like Voyager 1, Voyager 2, Cassini, and the Curiosity and Perseverance Mars rovers. They are extraordinarily reliable. They have no moving parts, but their power output is tiny, typically in the range of a few hundred watts at the start of mission, and it declines steadily as the plutonium decays with a half-life of approximately 87.7 years. After a century, a radioisotope thermoelectric generator produces roughly half its original output. After 2 centuries, a quarter. For a crewed starship requiring kilowatts or megawatts of continuous electrical power to run life support, lighting, food production, atmospheric processing, computing, communications, and propulsion systems, radioisotope generators are insufficient by orders of magnitude. Nuclear fission reactors offer substantially higher power output. Compact space-rated fission reactors have been designed and, in some cases, tested. NASA's Kilo Power project tested a prototype uranium-fueled reactor at roughly 1 kilowatt of electrical power, designed to scale to 10 kilowatts for surface power on the Moon or Mars. Scaled-up versions could potentially provide hundreds of kilowatts or even megawatts. But fission reactors require fuel, cooling systems, neutron moderators, control mechanisms, and radiation shielding of their own. Their fuel, typically enriched uranium, has a finite energy content. A reactor designed to run for 50 years must carry enough fuel for 50 years of sustained criticality, plus a safety margin. Fuel elements swell and degrade under prolonged neutron bombardment. Coolant loops corrode from the inside. Control rod mechanisms, if mechanical, wear. A reactor that must operate for a century without a complete overhaul is beyond any current engineering experience. The longest operating terrestrial reactors have operational lifespans of roughly 40 to 60 years, and they are maintained by entire industries of specialized technicians with access to global supply chains. Fusion power, the process that powers stars, would theoretically solve the energy problem for interstellar travel. Deuterium and helium-3 fusion could provide enormous energy densities with relatively manageable fuel mass. But controlled fusion for continuous power generation has not been achieved on Earth despite more than 70 years of research and billions of dollars in investment. Claiming that a Starship will run on fusion is currently a statement of hope, not engineering. Spare parts and onboard maintenance form the silent spine of Starship survival, the system beneath every other system. Every mechanical component aboard has a finite operational life. Bearings wear, seals degrade, pump impellers erode, valve seats corrode, electrical insulation becomes brittle under radiation exposure, circuit boards accumulate cosmic ray damage, solder joints fatigue under thermal cycling. Lubricants break down chemically and lose viscosity. Cable insulation cracks and creates short-circuit risks. Every one of these failures is predictable in a statistical sense. Engineers can estimate mean time between failures for most components, but stocking spare parts for every possible failure over a 50-year or 500-year voyage quickly becomes a mass and volume problem that overwhelms the ship's cargo capacity. 3D printing and additive manufacturing offer a partial solution. If the ship carries raw material feedstock, metal powders, polymer filaments, ceramic precursors, then a sufficiently capable fabrication system could produce replacement parts on demand. But 3D printing is not magic. Current additive manufacturing technology can produce functional parts in a range of materials, but achieving the metallurgical properties required for high-stress, high-temperature applications like turbopump impellers, reactor fuel cladding, or pressure vessel components remains extremely challenging. Printed metal parts often have different grain structures, porosity levels, and fatigue characteristics compared to conventionally manufactured components. A replacement part that looks identical to the original but fails after 1,000 hours instead of 10,000 hours creates a cascading maintenance burden that accelerates the ship's overall degradation, and fabrication requires expertise. Someone aboard must know how to design the replacement part, select the appropriate material, configure the printer, post-process the output, inspect it for defects, and install it correctly. That knowledge must be maintained and transmitted across generations of crew. If the fabrication specialist dies and their apprentice is only half-trained, the ship's manufacturing capability degrades. If the printer itself breaks and the crew cannot repair it, the entire maintenance chain collapses. The ship begins consuming its spare parts inventory with no way to replenish it, and every component that fails from that point forward becomes permanent damage. Micrometeoroid and interstellar dust hazards add an external threat that compounds the internal degradation. The interstellar medium is not perfectly empty. It contains roughly 1 atom per cubic centimetre on average, mostly hydrogen, along with scattered dust grains of varying sizes. At low velocities, this material is harmless, but a starship traveling at even a few % of the speed of light transforms every grain of dust into a hypervelocity projectile. A particle weighing 1 milligram, striking the hull at 5% of light speed, carries kinetic energy on the order of a large caliber bullet. At 10% of light speed, the energy scales quadratically and enters the range of small explosive charges. Over a voyage lasting decades, the forward-facing surfaces of the ship accumulate thousands or millions of such impacts. Each one erodes shielding, pits structural surfaces, damages sensor arrays, and weakens the hull's ability to contain atmosphere and resist subsequent impacts. Whipple shields, multi-layered impact barriers with sacrificial outer layers designed to vaporize incoming particles before they reach the pressure hull, are standard protection on current spacecraft. But Whipple shields designed for orbital debris at typical relative velocities of 10 to 15 kilometers per second may be inadequate for interstellar dust at thousands or tens of thousands of kilometers per second. The physics of hypervelocity impact changes dramatically at relativistic speeds. The incoming particle and the shield material both vaporize and produce plasma jets that can penetrate deeper than solid fragments. Designing shielding for these conditions requires materials science and impact physics that are currently at the edge of human knowledge, and the shield itself must survive the cumulative erosion of decades of continuous bombardment. Medical care aboard a starship must cover the full spectrum of human pathology without the infrastructure that makes modern medicine possible. On Earth, a patient with a complex fracture is treated in a hospital with imaging equipment, sterile operating rooms, and specialist surgeons backed by a pharmaceutical supply chain. On a starship, that patient is treated by whoever aboard has the most medical training, using whatever equipment and medications exist in the ship's inventory. The crew's medical needs will also evolve in ways that cannot be fully predicted at departure. Genetic disorders may emerge in crew members born aboard. Nutritional deficiencies may produce novel pathologies if the food production system cannot maintain a complete dietary profile. Psychological conditions, depression, anxiety, psychosis, and interpersonal violence must be managed in an environment where the patient cannot be separated from the community and where every individual is essential to the ship's operation. There is no evacuation. There is no specialist referral. The ship is the hospital, and the hospital never receives new equipment, new drugs, or new staff. The specific chemistry of pharmaceutical degradation makes this problem worse than a simple shelf life label suggests. Most medications are tested for stability over periods of 2 to 5 years under controlled storage conditions on Earth. Aboard a starship, those conditions do not exist. The ambient radiation environment accelerates the breakdown of complex organic molecules. Temperature fluctuations during thermal management cycles stress chemical bonds. Humidity variations in the recycled atmosphere alter dissolution rates. Antibiotics in the penicillin and cephalosporin families are particularly vulnerable, with some losing more than 50% of their potency within 3 to 4 years, even under ideal terrestrial storage. Epinephrine, a critical emergency medication, degrades predictably and becomes unreliable within roughly 2 years. Insulin, essential for any diabetic crew member, is notoriously temperature sensitive and cannot survive long-term storage without precise refrigeration that itself consumes power and requires maintenance. Cancer chemotherapy agents present perhaps the cruelest pharmaceutical problem aboard a starship. Given the elevated radiation environment, cancer incidence among the crew will almost certainly be higher than in any population on Earth. The drugs used to treat the most common radiation-induced cancers, alkylating agents, platinum compounds, and antimetabolites, are among the most chemically unstable medications in the entire pharmacopoeia. Many require reconstitution from powder immediately before administration. The powders themselves degrade. The sterile water required for reconstitution must be drawn from the ship's recycled supply, introducing contamination risks that would be unacceptable in any terrestrial oncology ward. A starship crew facing rising cancer rates may find itself equipped with medications that are expired, degraded, or simply gone, consumed by previous patients in previous decades. Surgery aboard a starship adds another dimension of impossibility. On Earth, even a moderately complex procedure requires a surgeon, an anesthesiologist, a scrub nurse, monitoring technicians, and a sterile environment with positive pressure air filtration. Aboard a Starship, the surgical team may consist of 1 or 2 people with cross-trained skills who also serve as engineers, farmers, or navigators. The operating space may double as a laboratory or examination room on every other day. Anesthesia depends on drugs with the same shelf-life vulnerabilities described above. Surgical instruments are finite and must be sterilized using equipment that itself requires maintenance. A single botched procedure can cost the ship a crew member whose expertise in another domain, reactor maintenance, crop genetics, or fabrication, may be irreplaceable. Beyond individual medical crises, a small sealed population faces a biological threat that operates on generational timescales. Genetic erosion. A Starship crew of even several hundred individuals represents an extremely limited gene pool. Over multiple generations, genetic diversity narrows. Recessive disorders that would be statistically negligible in a population of millions become increasingly likely to manifest when the same limited set of genomes recombines repeatedly. Immune system diversity, which depends on a broad range of human leukocyte antigen alleles distributed across the population, contracts. The crew becomes progressively more vulnerable to novel pathogens, including mutated strains of organisms they brought aboard themselves. Inbreeding depression. The general decline in biological fitness that accompanies reduced genetic diversity lowers fertility rates, increases infant mortality, and produces a population that is measurably less resilient with each passing generation. Managing this requires deliberate reproductive planning across centuries, which introduces ethical and social complexities that no human society has ever been forced to navigate under such constrained and irreversible conditions. Navigation and computing face a uniquely insidious form of degradation. In the inner solar system, a spacecraft fixes its position using the sun, known planets, and ground-based tracking stations. In interstellar space, none of these aids exist. There is no global positioning system. There are no ground stations. The ship relies entirely on measuring the angular positions of distant stars with onboard optical sensors and comparing those measurements against a stored catalogue to triangulate its own location. But the geometry of this problem changes as the ship moves. Stars that served as useful reference points at departure shift their apparent positions as parallax changes with the ship's displacement. Over a journey of several light years, the familiar constellations distort beyond recognition. The angular relationships between stars that defined the catalogue at launch no longer match what the sensors observe. The catalogue must be corrected in real time, using models of stellar proper motion, the actual physical movement of each star through the galaxy, which for some nearby stars is known precisely but for many others is estimated with significant uncertainty. A small error in the proper motion correction for a single reference star can propagate into a navigational drift of millions of kilometers over a transit lasting decades. Sensor calibration compounds the difficulty. Optical star trackers rely on semiconductor detectors that accumulate radiation damage over time. Individual pixels degrade or fail entirely, creating blind spots in the sensor's field of view. The optical elements, lenses and mirrors, develop micro-pitting from interstellar dust impacts and molecular contamination from slow outgassing within the instrument housing. Each of these effects introduces systematic errors that shift the apparent position of observed stars by tiny but cumulative amounts. Without an external reference to calibrate against, the crew cannot easily distinguish between a real navigational drift and a sensor artifact. The ship may believe it is on course when it has strayed, or it may attempt a correction that introduces a new error. The slow blindness of degrading sensors combines with shifting stellar geometry to create a navigational uncertainty that grows with every passing year of the voyage. Computing hardware is vulnerable to cosmic ray-induced single-event upsets, where a high-energy particle strikes a transistor and flips a bit in memory or corrupts a processor operation. In low Earth orbit, these events are relatively rare and are managed through error-correcting memory and redundant processors. In interstellar space, with higher radiation flux and no magnetic shielding from a planetary field, the rate of single-event upsets increases substantially. Over decades, cumulative radiation damage degrades semiconductor performance. Transistors become leakier. Threshold voltages shift. Clock speeds must be reduced to maintain stability. Storage media, whether solid state or magnetic, accumulate errors. The ship's computing infrastructure slowly becomes less reliable, less capable, and less trustworthy at exactly the point in the mission when accurate navigation and system monitoring are most critical. Propulsion system survival presents a paradox of dormancy. Many Starship concepts envision a high-thrust acceleration phase, followed by a long coast phase, followed by a high-thrust deceleration phase at the destination. The propulsion system must fire reliably at departure, then sit dormant for years or decades during the coast, then fire again with the same reliability at arrival. But mechanical and chemical systems do not survive long dormancy well. Unlike an engine that runs continuously and can be monitored for early warning signs, a dormant propulsion system sits in silence, accumulating invisible damage that reveals itself only at the moment of reignition, the one moment in the entire voyage when failure is most immediately catastrophic. There is no test fire between stars. There is no way to cycle the engines periodically without expending irreplaceable propellant. The crew must trust that a system which last operated decades ago will perform flawlessly on command. A propulsion system that works perfectly at departure may refuse to start after 50 years of cold, dark, irradiated dormancy. The specific failure modes are well documented in terrestrial engineering and multiply in the space environment. Residual propellant left in fuel lines after the acceleration phase can undergo slow chemical decomposition, producing solid crystalline deposits that block injector orifices with residue too fine to filter but too dense to flush. If the lines are purged instead, the elastomeric seals that maintain pressure integrity lose their plasticizers in hard vacuum, becoming brittle and developing micro-cracks that propagate imperceptibly over decades. Turbopump bearings, even in a dormant system, are subject to brineling, the formation of tiny permanent depressions in the bearing race caused by the static load of the rotor resting in one position for years. When the pump is finally commanded to spin, those depressions create vibration, accelerated wear, and potential seizure. Ignition systems that rely on pyrotechnic initiators face chemical aging of their energetic materials. Electrical ignition systems face insulation degradation and contact corrosion. Valve actuators, whether hydraulic or electric, suffer seal embrittlement and lubricant migration. Each of these failure modes is individually manageable in a system that is regularly inspected, maintained, and test-fired. In a system that has sat dormant in a high-radiation vacuum for half a century, they form a combined threat that no amount of pre-departure testing can fully predict. And if the engine will not fire for the deceleration burn, every decade of careful survival aboard the ship collapses into a single mechanical verdict. The destination exists, but the mission is over. Every one of these systems — air, water, food, shielding, power, spare parts, fabrication, medical, navigation, computing, and propulsion — degrades along its own timeline. But they do not degrade independently. They are coupled. Power loss reduces life support capacity. Life support degradation reduces crew health. Reduced crew health impairs maintenance quality. Impaired maintenance accelerates mechanical wear. Accelerated wear increases demand for spare parts. Spare part depletion reduces repair options. Reduced repair options allow further degradation of every system simultaneously. The Starship enters a feedback loop of declining capability, where each failure makes the next failure more likely, and the recovery from each failure less complete. This is not a single dramatic crisis. There is no explosion, no asteroid impact, no alien attack. It is a slow, compounding erosion of margin. Every year, the ship becomes slightly less capable than it was the year before. Every repair is slightly less effective than the last. Every system runs slightly closer to its minimum threshold. And somewhere in that long, quiet decline, the ship crosses a line that no one aboard can precisely identify. The moment when the mission transitions from difficult to doomed. Not because anything spectacular happened, because 1,000 small things wore out, each one too minor to justify alarm, each one contributing to a cumulative fragility that eventually becomes irreversible. The systems described here are not speculative. They are the same systems that keep the International Space Station alive in low Earth orbit right now, scaled up, stripped of all external support, and asked to function not for months but for lifetimes. Every engineer who has worked on life support in space understands that the challenge is not any single system. The challenge is all of them, running simultaneously, interacting in ways that cannot always be predicted, degrading on their own schedules, and demanding maintenance from a crew that has no backup, no supply line, and no option to shut down the machine and walk away. A Starship survives or dies on the performance of these systems. Speed determines how long they must hold, but the systems themselves determine whether speed matters at all. A ship that can reach 10% of light speed but cannot keep its water recycler running for 44 years will never arrive at Alpha Centauri. A ship that solves every engineering problem but cannot grow food for 500 years will never see TRAPPIST-1. The propulsion system sets the schedule. The survival systems decide whether the schedule is real, and those survival systems have never been tested at the scale, duration, or isolation that interstellar travel demands. Not once. Not in any laboratory on Earth or any habitat in orbit. Every estimate of their long-term performance is an extrapolation from data that covers, at most, a few decades of operation, under conditions far more forgiving than the void between stars. The next question is whether any destination in the galaxy is close enough to fall within those margins, and the answer depends on which star you are aiming for, because each one imposes a different sentence of survival. The stars do not arrange themselves for human convenience. They sit at distances that have nothing to do with how far we can travel, how long our machines can last, or how badly we want to reach them. Every famous point of light in the night sky carries its own survival sentence, and most of those sentences are longer than any human institution has ever endured. But the only way to understand what a real starship must survive is to walk the ladder one rung at a time, starting close and climbing outward, and to watch what breaks at each new distance. Alpha Centauri is where every interstellar conversation begins, and where most of them stall. It is the nearest star system to ours, a triple system consisting of two sun-like stars, Alpha Centauri A and Alpha Centauri B, locked in a mutual orbit, and a small red dwarf called Proxima Centauri that circles the pair at a much greater distance. Proxima is the closest of the three to Earth, sitting at approximately 4.24 light-years. The pair of larger stars lies slightly farther, at roughly 4.37 light-years. The system is real, the distance is confirmed, and Proxima Centauri is known to host at least one roughly Earth-sized planet, Proxima b, orbiting within what astronomers call the habitable zone. It is the most obvious target in the sky for an interstellar mission, and it is brutally far. At 10% of the speed of light, a velocity that no human technology can currently achieve or is on any funded path to achieving, a Starship would reach Alpha Centauri in approximately 44 years. That number sounds almost manageable. A human career, a long marriage, a lifetime of work, but a single lifetime. The crew who launched the mission might, with medical luck and radiation management, live to see the destination. It is the one interstellar target where the phrase, within a human lifetime, is not entirely dishonest. But 44 years of continuous operation for every critical system aboard the ship is not a modest engineering requirement. It is an extraordinary one. No closed-loop life support system has ever been tested for 44 years. No nuclear reactor designed for spacecraft has ever operated for 44 years without major overhaul. No sealed habitat has ever sustained human beings for 44 years without resupply. The International Space Station, the longest-running crewed habitat in history, has been continuously occupied for roughly 25 years, and it receives multiple resupply missions per year. A 44-year interstellar transit means every pump, every filter, every seal, every bearing, every circuit board aboard must either survive the entire journey or be replaced from onboard inventory. The spare parts manifest alone becomes an engineering project of staggering complexity. How many replacement water recycler membranes do you carry? How many backup scrubber cartridges? How many sets of turbo pump bearings? Every item you add increases the ship's mass, which increases the fuel required, which increases the reactor size, which increases the shielding mass. The engineering problem does not scale linearly. It compounds. And even if the engineering holds for every one of those 44 years, the destination itself may not deliver what the name promises. Proxima b, the roughly Earth-sized planet confirmed in the habitable zone of Proxima Centauri, is the most frequently cited reason to aim for this system. But the word habitable in the astronomical sense means only that the planet's orbit permits liquid water on its surface under certain atmospheric conditions. It does not mean the planet is hospitable, survivable, or remotely Earth-like in any practical sense. Proxima b is almost certainly tidally locked to its star, meaning one hemisphere bakes in permanent daylight, while the opposite hemisphere freezes in permanent darkness. The boundary between these regions, a narrow twilight strip called the terminator, is the only zone where temperatures might permit liquid water. But the atmospheric dynamics of such a world are poorly understood and may involve extreme wind patterns that render surface conditions violent and unpredictable. Worse, Proxima Centauri is an active flare star. It produces frequent and powerful stellar flares that bombard its planets with intense bursts of ultraviolet radiation and energetic charged particles. These events can be hundreds or thousands of times more intense than anything Earth experiences from our comparatively stable Sun. Over billions of years, this bombardment may have stripped Proxima b of whatever atmosphere it once possessed. Observations to date have not confirmed the presence of a substantial atmosphere. If the planet is a bare, irradiated rock with no magnetic field and no atmospheric shielding, it offers a Starship crew nothing except a closer view of an uninhabitable world they spent 4 decades reaching. A crew that arrives at Alpha Centauri after 44 years of mechanical endurance may discover that Proxima b cannot be settled, cannot be walked on without heavy radiation protection, and cannot support any form of long-term habitation without first constructing fully enclosed surface habitats on terrain that offers fewer natural resources than the lunar surface. The nearest potentially habitable world, the one that justified the entire mission, may turn out to be no more welcoming than the ship itself. The engineering triumph of arrival may deliver not a new home, but a new confinement, one with a view of a dim red dwarf star that intermittently tries to sterilize everything in orbit around it. This complicates even the first rung of the ladder. Alpha Centauri is not merely the nearest star system. It may also be the first demonstration that proximity guarantees nothing about habitability. A starship designed for settlement may need to carry everything required to build sealed habitats on an airless world, which means even more mass, even more spare parts, even more systems that must survive the journey, all for a destination that has not yet proven. It can offer anything a ship-bound crew could not already provide for themselves in open space. Alpha Centauri is the easiest destination on the interstellar ladder. It is the shortest journey, the smallest spare parts inventory, the fewest maintenance cycles, the lowest cumulative radiation dose, and it is already beyond anything humanity has ever attempted. Building a starship for Alpha Centauri is like building a bridge that must support its own weight for half a century while you are still crossing it, with no ground crew, no repair trucks, and no way to turn back if a cable snaps in year 30. Every rung above this one makes that bridge longer, heavier, and less forgiving. Barnard's star sits at approximately 5.96 light-years from Earth. It is the 4th closest individual star to our solar system, a dim red dwarf in the constellation Ophiuchus. At 10% of light speed, the journey takes roughly 60 years. That is 16 years longer than Alpha Centauri. 16 additional years of seal degradation. 16 additional years of radiation dose accumulation. 16 additional years of mechanical wear on every moving component aboard. 16 more years of food production, water recycling, and atmospheric management in a system that has never been tested for even a fraction of that duration. But Barnard's star introduces a survival problem that has nothing to do with the ship's machinery. It introduces the problem of destination value. As of the most current observational data, Barnard's star has no confirmed habitable planets. There have been candidate detections, signals in radial velocity data, that suggest a possible super-Earth orbiting the star, but these signals remain disputed and unconfirmed. A starship that departs for Barnard's star commits its crew to 60 years inside a sealed machine for a destination that may contain nothing worth studying, nothing worth settling, and nothing worth the sacrifice. The crew arrives, surveys a barren system with no atmosphere and no liquid water, collects data that a robotic probe could have gathered more efficiently, and faces the realization that their entire adult lives were spent in transit to a dead end. This is not an engineering failure. Every system aboard may have performed flawlessly. The air was clean, the water was pure, the food was adequate, the reactor ran within tolerance, and none of it mattered, because the destination was empty. The mission failed not because the ship broke, but because the universe did not put anything useful at the other end. Barnard's star teaches a lesson that every subsequent rung on the ladder reinforces. Survival is necessary, but not sufficient. The ship must survive, and the destination must be worth surviving for. Sirius is the brightest star in the night sky. It is visible from almost every inhabited region on Earth. Ancient civilizations tracked its movements with obsessive precision. It sits at approximately 8.6 light-years from our solar system, roughly double the distance to Alpha Centauri. At 10% of light speed, a Starship would need approximately 86 years to reach it. 86 years of continuous operation. The crew who launched the mission would not live to see its completion. The people who arrive at Sirius would be the children or grandchildren of the people who left Earth. This is the first rung on the ladder where the journey definitively spans more than one human lifetime. The implications cascade immediately. If the original crew dies during transit, who maintains the ship? Their children. But their children did not choose this mission. They were born into it, raised inside a sealed metal cylinder, educated by parents whose own expertise may have been incomplete or degraded by decades of isolation. The ship's maintenance protocols must be teachable. The engineering knowledge required to diagnose a failing coolant loop or recalibrate a star tracker must be transmitted from one generation to the next with perfect fidelity, because a single generation that loses a critical skill set creates a gap that cannot be filled. There is no university to send the next generation to. There is no technical library that updates itself. There is only the crew, teaching their children what they know, hoping that what they know is enough. Sirius also introduces a destination hazard that Alpha Centauri and Barnard's star do not. Sirius is a binary system. Sirius A, the bright primary star, is roughly twice the mass of our Sun and roughly 25 times more luminous. Sirius B, its companion, is a white dwarf, the collapsed remnant of a star that exhausted its nuclear fuel and shed its outer layers. White dwarfs are extraordinarily dense, extraordinarily hot, and capable of producing intense ultraviolet and X-ray radiation, particularly if material from a companion star falls onto their surface. A starship approaching the Sirius system must contend not only with the radiation from Sirius A, but with the complex and potentially hostile radiation environment created by the interaction between the two stars. Shielding that was adequate for the interstellar void may be insufficient for the close approach to a system where high-energy radiation sources orbit each other at distances comparable to the gap between our Sun and Uranus. Tau Ceti sits at approximately 11.9 light-years. It is a G-type star, roughly the same spectral class as our Sun, though slightly smaller, slightly cooler, and slightly less luminous. It has been a fixture of science fiction for decades, partly because of its solar similarity and partly because it is a single star without a close binary companion, making stable planetary orbits more plausible. Observations have identified candidate signals suggesting multiple planets in the system, some of which may orbit within the habitable zone, though none have been confirmed as rocky, Earth-sized, and definitively habitable. At 10% of light speed, Tau Ceti requires approximately 120 years of transit. This is the threshold where a starship must function not merely across generations, but across multiple generations. The crew that launches the mission will die aboard. Their children will likely die aboard. Their grandchildren may be the first to see the destination star as something more than a faint point of light, slightly brighter than its neighbours. By the time the ship arrives, the original mission planners will have been dead for decades. The language spoken aboard may have drifted. The cultural values of the crew may have shifted. The political or social structure that governed the first generation may have collapsed or been overthrown by the second or third. This is the survival problem that no amount of engineering can fully solve. It is the human problem. A sealed community of finite size, cut off from all external contact, must maintain social cohesion, institutional knowledge, and mission commitment for more than a century. Every historical example of isolated human communities suggests that this is extraordinarily difficult. Antarctic research stations, submarine crews, and remote colonial settlements all demonstrate predictable patterns of social fragmentation, knowledge loss, and cultural drift over timescales far shorter than a century. A Starship crew heading for Tau Ceti must somehow resist these forces for longer than the gap between the American Revolution and the present day. And the crew must do this while also maintaining the physical ship, which, by year 120, will have endured more than a century of continuous mechanical degradation in the most hostile environment human beings have ever attempted to survive. TRAPPIST-1 sits at approximately 40 light-years from Earth. It is an ultra-cool red dwarf star in the constellation Aquarius with only about 9% of the mass of our Sun. The system is famous because it hosts 7 known rocky planets, 3 of which orbit within the habitable zone. It is the most planet-rich system at a potentially habitable distance that astronomers have yet identified. James Webb Space Telescope observations have been studying whether any of these planets retain atmospheres, with results so far suggesting that some of the inner planets may have lost their original hydrogen-helium envelopes, but leaving open the possibility that secondary atmospheres of heavier gases like carbon dioxide could exist. The data is still incomplete. The question of whether any TRAPPIST-1 planet is genuinely habitable in the biological sense remains open. At 10% of light speed, the journey to TRAPPIST-1 takes approximately 400 years. 4 centuries of continuous operation, 4 centuries of atmospheric recycling, water recovery, food production, power generation, radiation shielding, and mechanical maintenance. The ship must survive longer than the entire period between the founding of the Jamestown colony and the present day. It must function longer than the Ottoman Empire lasted, longer than the Ming dynasty, longer than the gap between the invention of the printing press and the invention of the internet. At this distance, the Starship ceases to be a vehicle in any meaningful sense. It becomes a civilization. It must educate its children. It must govern itself. It must resolve conflicts without external authority. It must maintain agricultural productivity across centuries of continuous cultivation in a closed environment where soil nutrient cycling, plant genetics, and microbial ecology all evolve in ways that cannot be fully predicted at departure. It must maintain its own manufacturing capability, its own medical system, its own educational institutions, and its own sense of purpose across a span of time, so long that the mission's original rationale may become incomprehensible to the people actually living aboard. TRAPPIST-1 is the rung on the ladder where the engineering problem and the civilization problem become indistinguishable. You cannot solve one without solving the other. A ship with perfect machinery but a broken society will not arrive. A ship with a thriving community but failing reactors will not arrive. Both must endure for 400 years, in tandem, without any external input. No human project has ever achieved anything remotely comparable. The specific challenges of sustaining a 400-year civilization inside a sealed vessel extend far beyond abstract statements about duration. They are concrete and deeply human. Birth rates must be managed with a precision that no society on Earth has ever accepted voluntarily. Too few children and the population declines, skills gaps open, and the maintenance burden per surviving crew member rises until the remaining hands cannot keep the ship running. Too many children and the ship's caloric budget, water budget, and atmospheric processing capacity exceed their design margins. Every child born aboard is not merely a new member of the community. Every birth is a resource allocation decision with consequences that cascade across decades. The ship must sustain a population large enough to maintain genetic diversity and fill every critical skill role, but small enough to live within the hard physical limits of what the food production and life support systems can carry. This balance must be maintained not for a single generation, but for roughly 20 successive generations, with no tolerance for the demographic fluctuations that every civilization on Earth experiences naturally through famine, migration, and war. Vocational assignment introduces ethical questions that have no earthly parallel at this scale. The ship needs a specific number of reactor engineers, life support technicians, agricultural specialists, medical practitioners, fabrication operators, navigators, and educators in every generation. If a child shows aptitude for art but the ship desperately needs another water recycler technician, who decides? The parents? A governing council? an algorithm weighing skill inventories against projected system failures. On Earth, career choice is considered a fundamental expression of individual freedom. Aboard a Starship, a generation that produces too many philosophers and too few engineers is a generation that may kill the ship through neglect of critical maintenance. The tension between individual autonomy and collective mechanical survival has no clean resolution, and it recurs with every child born across 4 centuries. The psychological weight of being born into an unchosen mission is distinct from the psychological experience of volunteering for one. The first generation weighed the risks, accepted the losses, and found meaning in the sacrifice. A child born in Century 2 of the voyage has no such narrative of choice. The ship is simply the world. The mission is simply the condition of existence. There is no alternative life that child could have chosen, no road not taken, no comparison to a different reality. For some, this may produce acceptance. For others, it may produce a resentment directed at ancestors who made an irreversible decision on behalf of descendants who were never consulted. This resentment, if it becomes widespread, does not need to escalate into mutiny to be dangerous. It needs only to erode the willingness of enough critical personnel to perform their maintenance duties with full diligence, and the ship's slow mechanical decline accelerates from within. Recent James Webb Space Telescope observations have added a layer of uncertainty to the destination itself. Transit spectroscopy of the innermost TRAPPIST-1 planets, particularly TRAPPIST-1b and TRAPPIST-1c, has produced results consistent with these worlds possessing little to no atmosphere. A 2025 study of TRAPPIST-1d found the data satisfactorily consistent with no atmosphere at all, though a marginal possibility of one remains. TRAPPIST-1e, the planet most often cited as the system's best candidate for habitability, has proven more difficult to characterize. Early observations detected hints of methane, but follow-up analysis could not conclusively determine whether the signal originated from the planet's atmosphere or from molecular contamination in the photosphere of the host star itself. The question of whether any TRAPPIST-1 planet possesses a substantial, stable atmosphere remains genuinely open as of the most recent data. A Starship crew committing to a 400-year voyage toward this system would be wagering the existence of their entire civilization on an atmospheric detection that the most powerful telescope ever built has not yet been able to confirm. Vega sits at approximately 25 light-years. It is one of the brightest stars in the northern sky, a bluish-white main sequence star in the constellation Lyra. It is culturally famous, recognizable to almost any viewer, and carries associations with the search for extraterrestrial intelligence through the novel and film Contact. At 10% of light speed, the journey takes roughly 250 years. The survival problem that Vega exposes is not a new mechanical challenge or a new radiation hazard. It is the problem of mission coherence across deep time. 250 years ago, the world's dominant powers were colonial empires that no longer exist. The political map of every continent has been redrawn multiple times. The languages spoken in many regions have evolved so dramatically that a person from the 1770s would struggle to understand a modern speaker. Scientific understanding has transformed from Newtonian mechanics and phlogiston theory to quantum field theory and genomics. The social values, economic systems, and technological capabilities of the 21st century would be incomprehensible to someone from the 18th. A starship aimed at Vega must contend with the fact that this scale of transformation will occur aboard the ship and on Earth simultaneously but independently. The civilization that launched the mission will not be the civilization that exists when the ship arrives. The crew's descendants may have evolved their own language, their own values, their own understanding of the mission's purpose. Earth may have lost interest. Earth may have developed faster propulsion and sent a second mission that arrives before the first. Earth may have collapsed into a period of technological regression and forgotten the mission entirely. The ship arrives at Vega carrying the cultural cargo of a civilization that no longer exists anywhere in the universe except inside its own hull. Polaris sits at a distance that is genuinely difficult to state with precision because its parallax measurement carries significant uncertainty, but the best current estimates place it between approximately 323 and 433 light-years from our solar system. It is the North Star, the fixed point around which the northern sky appears to rotate, the navigational anchor for centuries of seafaring and overland travel on Earth. As a symbol, Polaris is the star of guidance, of direction, of finding your way home. As a destination, Polaris is absurd. At 10% of light speed, the journey would take more than 3,000 years. 3 millennia of continuous operation. The ship would need to outlast every empire, every religion, every nation, every language, and every institution that has ever existed in recorded human history. The people who arrive at Polaris would be separated from the people who departed by a span of time greater than the entire distance from the Bronze Age to the present. They would share no cultural reference with their ancestors. They would likely share no spoken language. Their social structures, their values, their understanding of themselves and their mission would have been transformed beyond recognition by thousands of years of isolated cultural evolution inside a sealed vessel. The engineering requirements at this duration become almost hypothetical. No material known to science has been tested for 3,000 years of continuous mechanical stress in a high radiation environment. No structure has been designed to maintain atmospheric integrity for 3 millennia. No computing system has been asked to remain operational for 30 centuries. The ship would need to be not merely maintainable but effectively rebuildable from the inside. A vessel that replaces itself component by component over thousands of years like a biological organism replacing its own cells, until nothing remains of the original structure except the continuity of function. Polaris is the rung on the ladder where the idea of a starship ceases to be an engineering challenge and becomes something closer to the entire recorded span of human civilization replayed inside a metal tube, multiple times over with no one watching from outside. Betelgeuse is not a destination. It is a warning. Betelgeuse is a red supergiant star in the constellation Orion, sitting at approximately 650 light-years from Earth. It is one of the largest stars visible to the naked eye, with a radius so immense that if it replaced our Sun, its surface would engulf Mars and stretch most of the way to Jupiter. It is also unstable. Betelgeuse has been observed dimming and brightening irregularly, shedding vast quantities of material from its outer layers, and exhibiting behavior consistent with a star in the late stages of its life. It is expected to explode as a supernova at some point in the astronomically near future, a time frame that could mean tomorrow or could mean 100,000 years from now. A starship aimed at Betelgeuse faces a uniquely existential problem. The destination itself may destroy itself before the ship arrives. A journey of 6,500 years at 10% of light speed gives the star ample time to undergo catastrophic change. The crew's distant descendants could arrive to find not a star system but an expanding shell of superheated gas and radiation, the remnant of an explosion that occurred centuries before they got there. The mission would not merely fail, it would be annihilated by the target. Betelgeuse teaches the hardest lesson on the ladder. The universe is not static. Stars are not permanent fixtures waiting for humanity to visit them. They are born, they age, they change, and they die on timescales that overlap with the travel times of any plausible starship. A mission that assumes its destination will still exist upon arrival is making a bet against astrophysics, and the longer the journey, the worse the odds become. Gliese 710 offers the strangest twist on the entire ladder. It is not a star we travel to, it is a star that is travelling to us. Gliese 710 is an orange dwarf star currently sitting approximately 62.3 light-years from Earth in the constellation Serpens. It has roughly 58% of our Sun's mass and only about 4.5% of its luminosity. It is far too dim to see with the naked eye. By every ordinary measure, it is an unremarkable star, the kind of object that populates catalogues by the millions without attracting attention. But Gliese 710 is heading toward our solar system at approximately 14.5 kilometers per second. It is one of the best studied examples of a star on a direct approach trajectory. Data from the European Space Agency's Gaia spacecraft, refined through multiple data releases, has narrowed the prediction with remarkable precision. In approximately 1.29 million years, Gliese 710 will pass within roughly 10,500 astronomical units of our Sun. That is approximately 1/6 of a light year. It is about 1/25 of the current distance to Proxima Centauri. At its closest approach, Gliese 710 will be one of the brightest objects in the night sky, outshining Sirius, rivaling Jupiter in brilliance, visible to the naked eye as one of the most striking stellar objects ever seen from Earth. At first glance, this seems like the ultimate gift to interstellar travel, a star coming to us. The distance shrinks from 62 light-years to a fraction of a light-year. Surely a Starship launched at the right moment could reach Gliese 710 in a matter of years rather than centuries. But the gift dissolves under scrutiny. The approach takes 1.29 million years. That wait is longer than the entire existence of the species Homo sapiens. No civilization, no institution, no language, and no species has ever persisted for that duration in recognizable form. Waiting for Gliese 710 is not a strategy. It is a geological fantasy. The star will arrive, but nothing about present-day humanity will be around to greet it. Whatever civilization exists on Earth in 1.29 million years, if any exists at all, will make its own decisions about Gliese 710 with technologies, values, and knowledge that bear no relation to anything we can imagine today. And even if a Starship were launched during the window of closest approach, the encounter itself is brief in cosmic terms. Gliese 710 passes through the outer reaches of the solar system at 14.5 kilometers per second and continues onward. It does not stop. It does not orbit. It passes like a ship in the night, crossing through the Oort cloud and continuing into the void beyond. A mission to Gliese 710 during its flyby would need to match velocities with a moving target, study a system in transit, and deal with the gravitational disruption the star's passage may cause to the outer solar system's population of icy bodies. The encounter would likely send showers of comets cascading into the inner solar system over millions of years, a consequence that dwarfs any scientific benefit the flyby might offer. Gliese 710 is not a destination. It is a reminder that even cosmic proximity is measured on timescales that mock human ambition. The universe occasionally brings stars closer, but it does so on its own schedule, indifferent to whether anyone is ready to take advantage. The ladder of stars does not end with Gliese 710. It extends outward through the entire galaxy, past thousands of stellar systems at tens, hundreds, and thousands of light-years. Each additional light-year multiplies every survival challenge aboard the ship. The radiation dose climbs, the mechanical wear accumulates, the spare parts inventory depletes, the food production system ages, the crew population turns over, the institutional knowledge erodes, the mission's connection to its origin fades, and at every rung the same question recurs with increasing urgency. Is the destination worth what it costs to reach it? Alpha Centauri demands 44 years of flawless mechanical survival. Barnard's star demands 60 years and the acceptance that the destination may be worthless. Sirius demands 86 years and the first generational handoff of crew. Tau Ceti demands 120 years and the maintenance of social cohesion across multiple generations. Vega demands 250 years and the preservation of mission coherence across a span that exceeds most civilizations. TRAPPIST-1 demands 400 years and the construction of a functioning civilization inside a sealed vessel. Polaris demands 3,000 years and the effective reinvention of the ship from the inside, multiple times over. Betelgeuse warns that the destination itself may not survive the journey, and Gliese 710 reminds us that even the cosmos's generosity operates on timescales that dwarf any human plan. The pattern is merciless. Every star reveals a new way the mission can fail, not because the ship breaks, but because the challenge exceeds the duration for which any human system, mechanical, biological, social, or institutional, has ever been sustained. The question is no longer which star to aim for. The question is whether any duration of survival is achievable at all. And behind that question sits a deeper one, the question that no amount of engineering can answer. Even if the ship survives, even if the systems hold, even if the crew endures, even if the destination is real and reachable, there remains the possibility that the mission itself will have lost its meaning long before the ship arrives, that the civilization that launched it will have changed beyond recognition, or vanished, or sent a faster vessel that got there first, or simply stopped caring. That the Starship will drift on, perfectly functional, carrying a community of human beings whose purpose evaporated centuries ago, while they were in transit, still alive, still maintaining, still surviving, but no longer certain why. That question does not belong to engineering. It belongs to something harder, and it is waiting at the end of the ladder. Suppose the ship survives. Suppose every engineering problem described up to this point is solved. Suppose the water recycler holds at 99.8% closure for a century. Suppose the carbon dioxide scrubbers maintain atmospheric composition within safe margins for 500 years. Suppose the nuclear reactor operates within tolerance for the entire voyage, cooled by a system that was designed to function without overhaul for longer than any reactor on Earth has ever run. Suppose the food production bays yield adequate calories generation after generation, the hydroponic trays cycling through crop rotations calibrated to sustain a population that was carefully calculated at departure. Suppose the radiation shielding holds. Suppose the spare parts last and the 3D printers keep working. Suppose the hull withstands interstellar dust erosion. Suppose the propulsion system, dormant for decades, fires cleanly when it is time to decelerate. Suppose all of this works. Every system, every subsystem, every replaceable component, every biological cycle aboard the ship performs within the margins required for survival across the full duration of the voyage. The ship arrives at its destination star. It decelerates successfully. It enters orbit around a planet or parks itself in a stable position within the system. The crew is alive. The vessel is functional. The mission, by every mechanical and biological metric, is a success. Now ask the harder question. Does anyone still care? The civilization that built and launched the Starship existed at a specific moment in human history. It had specific values, specific scientific priorities, specific economic structures, and a specific understanding of what the mission was supposed to achieve. That civilization funded the mission. It trained the crew, it designed the ship, it loaded the cargo, it celebrated the launch, and then it watched the ship shrink to a point of light and disappear into the dark. In the years after departure, the ship sends status reports. They arrive on Earth after a delay measured in years. The first reports are front-page news. The second round generates academic interest. The third round is noted in specialized journals. By the 10th report, a generation has passed on Earth. The political leadership that championed the mission has been replaced. The space agency that managed it has been reorganized. The funding model has changed. New technologies have emerged that make the ship's systems look primitive. A new telescope, vastly more powerful than anything available at launch, has already imaged the destination system in detail that rivals what the ship's instruments could achieve at close range. The scientific data the Starship was designed to collect has been partially or wholly superseded by observations made from Earth orbit at a fraction of the cost. By the time the ship reaches the halfway point, Earth has been living without it for decades. The crew's families have aged, died, and been succeeded by descendants who never met the original astronauts. The cultural moment that made the mission feel necessary has passed. The political consensus that supported it has dissolved. The language of the mission's original charter has become archaic. The Starship is no longer a national priority or a civilizational ambition. It is a historical footnote, an expensive artifact of a previous era's optimism, still transmitting faintly from an unimaginable distance, but no longer occupying any meaningful place in the public consciousness. And this is the optimistic scenario. The pessimistic scenario is worse. Earth may experience technological regression. Wars, pandemics, economic collapse, or environmental catastrophe could degrade the technological base required to maintain the deep space communication network. If the institutions responsible for that support collapse, the signal from the Starship simply goes unheard. The ship continues transmitting into silence, unaware that no one is listening. Or Earth may experience technological acceleration. A breakthrough in propulsion physics, achieved 50 or 100 years after the Starship's departure, may enable a second mission traveling at significantly higher speed. The second ship overtakes the first. It arrives at the destination decades or centuries before the original mission. The crew of the first ship, still in transit, still maintaining their vessel with painstaking daily effort, eventually receives a transmission from the destination system, informing them that humans have already arrived, settled, studied, and possibly moved on. Their entire voyage, Their entire sacrifice, their entire generational commitment to survival has been rendered redundant by a civilization that simply waited a little longer and built something faster. This is not a hypothetical concern. It has a name. Physicist Robert Forward discussed the problem decades ago, and researcher Andrew Kennedy formalized it as the weight calculation. Kennedy demonstrated mathematically that for any given rate of improvement in propulsion technology, there exists an optimal departure date. Launch too early and the ship is overtaken. Launch too late and you waste time in waiting. For distant targets, the math often suggests waiting for centuries because the improvement in speed gained by delaying launch more than compensates for the time spent waiting. The implication is devastating. For many interstellar destinations, the rational decision is not to launch at all. Not yet. Not until propulsion technology matures to the point where the transit time drops below the expected wait time for the next breakthrough. A Starship launched today toward a star, 40 light-years away, may be overtaken by a Starship launched in 80 years that arrives in 40. The crew of the first ship spent their lives aboard a vessel that was obsolete before it reached the halfway mark. Their children were born into a mission that was already redundant. Their grandchildren arrive at a destination where the welcome committee speaks a different language and uses technology that makes the first ship look like a wooden canoe. And the crew may know this. The communication delay makes real-time updates impossible, but over the course of a multi-century voyage, news from Earth trickles in with increasing delay but never stops entirely, at least not as long as someone on Earth is still transmitting. The crew may receive, years after the fact, reports of propulsion breakthroughs that imply their mission will be overtaken. They may receive confirmation that a second, faster ship has been launched. They may receive silence, which could mean anything, that Earth lost interest, that Earth lost capability, or that Earth is simply too far away for the signal to be detected by the ship's aging communications array. Each of these possibilities corrodes the single most important resource aboard the ship, the one that no engineering diagram includes and no spare parts manifest accounts for: purpose. A human being can endure extraordinary physical hardship if they believe the hardship has meaning. Crews can survive isolation, deprivation, danger, and loss if they share a conviction that their suffering serves a goal larger than themselves. This is the psychological foundation of every military unit, every polar expedition, every long-duration submarine deployment, and every crewed space mission in history. The mission gives the suffering a frame. The frame makes the suffering bearable. Remove the frame and the suffering becomes pointless. A Starship crew that learns their mission has been rendered obsolete does not merely experience disappointment. They experience a collapse of the psychological architecture that has sustained them, their parents, and possibly their grandparents through decades of confinement, sacrifice, and risk. Why maintain the water recycler if someone else already arrived? Why educate the next generation in stellar cartography if the destination has already been mapped? Why endure the radiation, the confinement, the rationing, the endless mechanical vigilance if the entire endeavour has been overtaken by history? Some crews might adapt. They might redefine the mission. They might choose to continue for the sake of the journey itself, or for the community they have built, or for the knowledge they carry. But psychological research on isolated groups suggests that purpose loss is among the most destructive forces a small community can experience. It does not produce orderly redefinition. It produces depression, conflict, substance abuse where substances are available, withdrawal from communal responsibilities, and, in extreme cases, violence. A Starship that loses its purpose does not gently transition into a philosophical commune drifting between the stars. It fractures. And fractures aboard a sealed vessel with no escape route are not metaphorical. They are lethal. Even without the obsolescence problem, purpose erodes naturally over generational timescales. The first generation aboard the Starship chose to go. They believed in the mission. They accepted the risks. They understood what they were leaving behind and what they hoped to reach. The second generation was born into the mission but raised by people who remembered Earth, who could describe sunlight and rain and open sky, who carried the emotional weight of departure. The third generation has no such connection. Earth is an abstraction, a word in a history lesson, a fading photograph in a digital archive. The destination star is equally abstract, a point of light that looks no different from any other through the ship's observation windows. The third generation lives entirely within the ship. The ship is their world, their home, their entire reality. They did not choose the mission. They inherited it, and the values of the civilization that launched the mission may feel as alien to them as the values of ancient Mesopotamia feel to a modern teenager scrolling through a phone. This cultural drift is not a failure of education or parenting. It is a consequence of isolation. Human cultures evolve through contact with other cultures, through trade, migration, conflict, and exposure to different ways of living. A Starship crew has no such contact. Their culture evolves in a sealed environment, responding only to internal pressures, resource allocation, governance disputes, interpersonal dynamics, generational tension, and the slow accumulation of traditions that have no reference point outside the hull. Over centuries, the shipboard culture may diverge so dramatically from the culture of departure that the mission's original goals become incomprehensible. The crew may develop their own religion, their own mythology, their own understanding of why they are aboard and where they are going. That understanding may bear no resemblance to the scientific rationale written into the mission charter at launch. Knowledge preservation is the institutional version of this problem. A Starship must carry not only the technical manuals for every system aboard, but the educational infrastructure to produce people capable of reading, understanding, and applying those manuals. This means schools. It means teachers trained to teach engineering, medicine, agriculture, navigation, computing, and fabrication. It means a curriculum that remains relevant across centuries of technological evolution within the ship. It means a system for identifying talent, training specialists, and ensuring that critical expertise is never concentrated in a single individual whose death could create an irrecoverable skills gap. Libraries help, digital archives help, but knowledge is not merely information stored on a medium. Knowledge is the capacity to interpret, apply, and extend information in novel contexts. A crew member who can read a reactor maintenance manual is not the same as a crew member who understands reactor physics well enough to diagnose an unexpected failure mode, not covered by the manual. The difference between stored information and living expertise is the difference between a cookbook and a chef. A Starship needs chefs, not cookbooks, and producing chefs requires a living educational tradition that must be sustained for the entire voyage. If that tradition breaks, if a generation fails to produce enough qualified reactor engineers or life support technicians or medical practitioners, the consequences are not felt immediately. They are felt a decade later, when the systems maintained by the previous generation of experts begin to fail and the current generation lacks the depth of understanding to repair them. The ship does not collapse suddenly. It enters the same slow, grinding decline described earlier, except now the cause is not mechanical wear but human institutional failure. The parts may be available, the tools may be functional, but the hands holding the tools do not know enough to use them correctly. Governance aboard a Starship is another problem without historical precedent at the required scale. Every human community requires some form of authority structure to allocate resources, resolve disputes, enforce rules, and make collective decisions. On Earth, governance structures are backed by external forces, legal systems, police, military, economic incentives, and the simple option of leaving a community you disagree with. Aboard a Starship, none of these external supports exist. The crew cannot leave, they cannot appeal to a higher authority, they cannot emigrate to a neighbouring community. They are locked inside a vessel with the same group of people for the rest of their lives, and the rest of their children's lives, and the rest of their grandchildren's lives. Every form of governance humanity has ever invented, democracy, monarchy, theocracy, oligarchy, meritocracy, has eventually failed, transformed, or been overthrown. Most last less than a few centuries, many less than a few decades. A Starship requires a governance system that functions reliably for the entire duration of the voyage, which for distant targets means centuries or millennia. No political scientist, no historian, and no constitutional theorist has ever proposed a system of governance that can be credibly expected to endure for that duration without experiencing revolution, authoritarianism, fragmentation, or collapse. The crew of a multi-century Starship will, with near certainty, experience at least one political crisis severe enough to threaten the mission. How that crisis is resolved, and whether the resolution preserves the ship's operational capability, may determine whether the mission survives more decisively than any mechanical failure. The arrival problem adds a final mechanical cruelty to the human and institutional challenges. Deceleration at the destination requires roughly as much energy as the initial acceleration. A starship that burned half its fuel to reach cruising speed must burn the other half to slow down. If the propulsion system has degraded during decades or centuries of dormant coasting, the deceleration burn may be partial, inadequate, or impossible. A ship that cannot decelerate becomes a flyby mission by default. It screams through the destination system at thousands of kilometers per second, its instruments gathering a few hours of close-range data before the star recedes behind it and the void swallows it again. The crew has survived everything, the ship has endured everything, and the reward is a brief glimpse of a star system through a window, followed by an eternity of coasting into the dark with no second destination and no way home. Magnetic sail deceleration, using the interaction between a superconducting loop and the charged particles of the interstellar medium, or the destination star's stellar wind to generate drag, has been proposed as an alternative that requires no onboard fuel. The concept is physically plausible but entirely untested. The braking force depends on the density of the medium, which varies between different trajectories and between the interstellar void and the region near a star. A magnetic sail designed for one set of conditions may perform differently in practice, producing less deceleration than expected or generating structural loads that exceed the sail's design limits. Trusting a multi-century mission to an untested braking system is a gamble with stakes that cannot be overstated. If the sail fails, every year of survival, every generation of crew, every calorie of food grown, and every litre of water recycled has been spent reaching a place the ship cannot stop at. And then there is the possibility that should trouble every honest conversation about starships more than any mechanical failure or social collapse. The possibility that the ship arrives, decelerates successfully, enters the destination system, surveys the available planets, and finds nothing, no habitable world, no atmosphere thick enough to breathe, no liquid water on any surface, no magnetic field to shield a settlement from stellar radiation. The candidate planets that looked so promising through telescopes from 40 light-years away turn out to be barren rock, or tidally locked furnaces, or ice-covered worlds with subsurface oceans locked beneath kilometers of frozen crust. The destination is real, the star is there, the planets are there, but there is nowhere to land, nowhere to live, and nothing to do except collect data and transmit it back to an Earth that may or may not still be listening. The ship has survived, the crew has endured, every system has held. And the mission has failed anyway, not because anything broke, but because the universe simply did not cooperate. The habitable world that the mission was designed to reach does not exist. The crew is alive inside a functioning starship, orbiting a dead system, 40 light-years from a home they can never return to, carrying the institutional memory of a civilization that launched them toward a hope that turned out to be empty. This is the final horror of interstellar travel, and it is the one that no amount of engineering, no amount of social planning, and no amount of psychological preparation can eliminate. A real starship does not merely need to survive the void. It needs the void to contain something worth surviving for. And that is a question that cannot be answered at departure. It can only be answered at arrival, after everything has already been spent. Every conversation about reaching the stars eventually arrives at a moment of forced honesty. The moment when the romance of the idea collides with the physical reality of what it would require. Not the glossy science fiction version, where sleek vessels glide between systems with artificial gravity and faster-than-light communication and medical bays that cure any ailment. The real version, the version where a starship is a pressurized metal container filled with recycled air, recycled water, recycled waste, and a small community of human beings who must keep every mechanical system aboard functional for longer than most civilizations have existed, with no help coming from anywhere, aimed at a destination that may not deliver what was promised. A real starship would be one of the most fragile and ambitious objects a civilization could ever construct. Not fragile in the sense of delicate, fragile in the sense of dependent on every seal holding. Every reactor running, every crop growing, every generation learning what the previous generation knew, every political crisis resolving without destroying the ship's operational capability, every medical emergency being treatable with what is aboard, every navigation fix being accurate enough to matter, every year of the voyage being survived well enough that the next year remains possible. The ship is not a symbol of escape. It never was. It is a test. A test of whether a machine built by human hands can keep running for longer than anything humans have ever built. A test of whether a biological life support system can maintain a closed loop for longer than any ecosystem has ever been sealed. A test of whether a human community can remain cohesive, functional, and purposeful for longer than any human community has ever endured in isolation. A test of whether a civilization can commit to a project whose completion lies beyond the lifespan of every person who approved it, every engineer who designed it, and every taxpayer who funded it. Right now, 5 spacecraft are on interstellar trajectories. Voyager 1 and Voyager 2 have crossed the heliopause and are drifting through interstellar space. Pioneer 10 and Pioneer 11 are following. Though contact with both was lost years ago, New Horizons is headed outward past the Kuiper Belt. All 5 are tiny, crewless, coasting without propulsion. None will reach another star for tens of thousands of years. They carry no life support, no food, no water, no crew. They are messages in bottles, tossed into an ocean so vast that the bottles will drift for longer than human civilization has existed before they pass within even a few light years of another star. A real starship would be something enormously more ambitious than those 5 drifting machines, and enormously more vulnerable. It would carry life. It would carry the expectation of return, if not for the crew, then for their data, their discoveries, their proof that the journey was possible. It would carry the weight of being the single most expensive, most complex, and most consequential engineering project in the history of the species. And it would carry that weight in absolute silence, in absolute darkness, in a place where the nearest source of help is not just far away but getting farther with every passing second. The stars are not going anywhere. They will burn for billions of years. Some will die and be replaced by others. The galaxy will continue its slow rotation, and the distances between stars will shift by fractions of a light year over millions of years, but the basic architecture of the night sky will persist for longer than any conceivable human future. The stars are patient. They do not require us to visit them. They do not reward us for trying. They simply exist at distances that test the absolute limits of what machines, bodies, and civilizations can endure. The question this story has tried to answer is not whether a starship can be built. Given enough time, enough resources, and enough determination, some version of a starship will almost certainly be attempted. The question is how long it can survive. And the honest answer is that nobody knows, not because the physics is unclear, but because the test has never been run. No machine has ever been asked to operate for centuries without external support. No biological system has ever been sealed for that long. No human community has ever been isolated at that scale for that duration. Every estimate is an extrapolation. Every projection is a guess built on data that covers a tiny fraction of the required timeline. What we do know is this: a real starship would not be defined by its speed. It would be defined by its endurance, by whether the air stays breathable in year 80, by whether the reactor still runs in year 200, by whether the children born in Century 3 still understand why the ship left home, by whether the hull holds against the slow erosion of dust and time and radiation, by whether the crew, whoever they have become after generations of sealed isolation, still possesses the knowledge, the will, and the institutional coherence to operate the deceleration burn when the destination star finally grows from a point of light into a disk. A starship is not a vehicle that crosses a distance. A starship is a machine that must outlast its own obsolescence, survive its own decay, preserve its own purpose, and carry a fragment of human civilization through a silence so deep and so long that the civilization it left behind may not exist by the time it arrives. That is what it means to build a real starship. Not faster engines, not better fuel. A fact, not a more efficient reactor. It means building something that can survive being alone for longer than any human project has ever had to endure. A sealed world thrown into the dark, with everything it will ever need already aboard, and nothing ahead of it but distance, time, and the quiet, indifferent patience of the stars.